Hi everyone, I'm Mohammed. I want to start by apologizing for not being able to be there in person to give the talk, but hopefully this works. The title of the talk is Locked Circuit Indistinguishability, a Notion of Security for Logic Locking. I want to acknowledge my co-authors, Siddharth, Mahesh, Mariana, Nahid, and John. So what is logic locking? The simplest way to put it is it's the hardware equivalent to password protection for software applications. So say you have a design for a chip that you would like to make, but you don't have the resources to manufacture a chip, so you decide you're going to outsource fabrication to a third-party facility. Unfortunately, if you share the design with the facility in the clear, there is the possibility that they might make more copies of it than requested by you and sell them later for the profit margin. So what do? One way to go about it is to lock the design so it doesn't function correctly unless activated with a certain key. And this is an example of what that might look like. This is one of the first mechanisms that was proposed for this purpose. The idea here is you select a number of wires in the circuit at random, where the number of wires you select is your security parameter. For each wire, you first flip a coin, and depending on the result of the coin flip, you insert either an XOR or an XNOR gate into the wire. Now you hope, unless the correct key bit is applied to each of these gates, the design is not going to function correctly. Of course, unless you transform the circuit further, the fabrication facility can figure out the correct key bit for each gate just by looking at the gate type. So the paper suggests that the designer can move bubbles up and down the circuit using De Morgan's laws, but it doesn't specify a concrete way for doing so. This mechanism, along with several others proposed after, turned out to be susceptible to a so-called SAT attack. In this attack, the adversary, which in our case is the third-party fabrication facility, waits for the designer to inject the chip into the market. They then acquire one copy of the chip. So that's this guy right here, and use a SAT solver to figure out what the secret key is based on the input-output behavior of the purchased chip. The technique here is to apply one input pattern to the chip, use the SAT solver to constrain the search space based on the observed output, then keep doing this until we zero in on a set of keys that yield functional equivalent circuits, at which point we just select one of these keys and use it to unlock the design. This attack has been the subject of so much study related to the idea, and defending it seems to open more problems than it solves. So just to give you a sense of the types of solutions that have been considered, I'm going to walk you through one example. So this paper was published 2 years after the SAT attack paper was published. It was an attempt to defend against the attack. So what's going on here? We have our key, we have the input. So this mechanism basically just checks whether the key is equal to the input. If they're equal, the output of the circuit is flipped. So we need to make sure that the output is not flipped for the correct key. So this masking circuit right here just checks whether the key is correct. If the key is correct, the flip signal is disabled. So why does this defend against the SAT attack? Let's look at the truth table of the circuit. So here we have the 3 inputs. So our circuit only has 3 inputs. The truth table of the correct circuit is going to have 8 rows. And here we have the output of the circuit for different key values. So here we're assuming the key is also 3 bits long. So that's the actual output of the circuit. And each of these columns tells us what the output of the circuit would be if the corresponding key is applied. So you will notice that to actually isolate the correct key, you need to apply at least 7 input patterns to the functioning chip. And that's simply because each of the incorrect keys differs from the correct key at exactly one input, and that input is distinct for each key. So what's wrong with this mechanism here? Well, first of all, the correct circuit, the thing we're trying to protect, is sitting out there in the clear. So an adversary looking at this can basically just extract the this logic code here and sell the extracted intellectual property for profit, defeating the purpose of logic locking. Even if that turns out to be hard, we have this masking circuit here, which, remember, just checks whether the input key is equal to the correct key. And it presumably just has a comparator within that does the checking. And that comparator would have the correct key value just sitting out there. So this can easily be mitigated by applying a point function obfuscator to this block here. So a point function obfuscator just takes a password checking circuit like this masking circuit here and hides the value of the correct key. Constructions for such obfuscators exist with provable security. So the problem of the key being there in the clear can be mitigated using cryptographic primitives. But even if we do so, remember, each incorrect key differs from the correct key at exactly 1 point. So an adversary can just select a key at random from the key space and obtain a circuit that performs approximately the same function as the correct circuit. It's almost undetectable by an end user unless they know what the key chosen by the adversary is. So that's another problem with this mechanism. This just tries to illustrate the point that as simple as defending from the SAT attack apparently is, it seems to open more problems than it solves. It seems to introduce, defending against the SAT attack seems to open the door for other kinds of attacks. So the question is, how do we design a mechanism that would render all attacks, infeasible? We borrow from the long-standing field of cryptography. We observe that the security guarantees that seem to be needed from logic locking is to make a circuit into a black box, so the fabrication facility doesn't get any advantage by having the lock design. So we set it as an objective to construct a locking mechanism that makes a design just so, a virtual black box. We start from a published mechanism known as ttlock. So this mechanism negates the output of the circuit at an input pattern selected at random from the input space. That input pattern becomes our secret key. So the modified logic cone here differs from the correct circuit at exactly one input. If we look at the truth table of the locked circuit here, that would be the truth table of the modified logic cone. As you can see here, it differs from the correct circuit at exactly one input, which is input pattern number 6. To restore the functionality of the circuit, we wait for the correct key to appear, and we check if the input is equal to the correct key. If that's the case, we flip the output of the circuit to get the correct output. This mechanism has the property that each input eliminates exactly one key from the solution space. So for example, input pattern number 4 eliminates exactly one input from the search space, which is key K4. So it's supposedly secure from the SAT attack. Now we argue against that in the paper. I'm not going to talk about here. I'll refer you to the paper for details on why we don't really think that ttlock is secure against the SAT attack. So how is this modified logic cone obtained? As you can see here, it's simple, right? So you just check if the input is equal to the secret key, and if that's the case, you flip the output using an XOR gate. Now, this mechanism obviously has well, two issues. Again, just like Starlock, the original logic call is sitting out there in the clear, and we also have a comparator here that presumably would reveal the value of the secret key if the adversary were to look at it. So the TT-Log paper proposes to do resynthesis on this whole circuit here. If you're not familiar with the concept, synthesis is a step in the chip design process that takes a high-level description of a circuit's behavior and turns that into an implementation in the form of logic gates. So the TT-Log authors use synthesis as an obfuscation mechanism. And they claim that doing so should be enough to conceal both the structure of the original circuit and the value of the secret key. Instead of negating the output at a single point, we choose to corrupt the whole truth table of the circuit in a random fashion. We do this by XORing the circuit output with a pseudo-random function. The key to the function becomes our secret key. We then apply an indistinguishability obfuscator to this part here. Just as a reminder, an I/O or indistinguishability obfuscator ensures that any two circuits that compute the same function come out the same when obfuscated. And as you may know, this combination of a pseudo-random function and an indistinguishability obfuscator has proven to be powerful, as Amit Sahai and others show in their 2013 Fox paper. So in that paper, they show that you can use a puncturable PRF, I'll explain what that is in a minute, and an indistinguishability obfuscator to construct all sorts of cryptographic primitives, including deniable encryption, which has been an open problem for quite some time. But how do we prove that this combination is useful in our setting? We'll get to that, but before we do, note that if the attacker chooses to apply a random key to our locked circuit here, they would get a circuit that computes a pseudo-random function, unlike TT-Log and Starlock, where they would get a circuit that computes almost the same function as the correct circuit. So we don't have the same problem as Starlock and TT-Log. But that is not all we need. Remember, what we really need is a mechanism that renders the circuit a virtual black box. So how do we prove that applying an indistinguishability obfuscator to our corrupted circuit makes it that? The answer to this question is implicit in a paper by Canetti et al. In this paper, Canetti and others show us how to construct an obfuscator for probabilistic circuits. These are circuits that flip coins as part of their operation. They prove the security of their construction using a fantastic technique, which turns out to be applicable for us as well. We'll first assume that our pseudo-random function is puncturable, meaning given any key and a point in the domain, we can puncture the key so it allows for evaluating the PRF on all inputs except the puncturing point. Puncturable PRFs can be constructed from the GGM construction, again in an elegant manner, and I'll be happy to show you how to do so in the question period if you're interested. We're also going to assume that both the puncturable PRF and the indistinguishability obfuscator are sub-exponentially secure, which means that the chance of an adversary breaking either primitive is at most a sub-exponential in the security parameter. Epsilon here is any number between 0 and 1. In the case of the PRF, the security parameter would be the key length, and in the case of the I/O, it would be the size of the larger of the two circuits. So this assumption basically means that both primitives are really, really secure. They need to be secure enough for our property to hold. So what's the idea behind the proof? We're going to leverage the fact that both our component primitives are sub-exponentially secure to show we can transform a locked circuit into a plausible locked version of any other circuit without an adversary having more than negligible advantage in telling the difference. Indistinguishability of locked circuits in turn gives us the virtual black box property. So let F and G be any two circuits. We're going to start by showing that we can change the output of F at any point to that of G without an adversary having more than sub-exponential probability of telling that we have done so. And we're going to rely on the sub-exponential security of both our primitives here. So to do this, we're first going to puncture the PRF key K star at the puncturing point X star. So the key we get is going to be good for evaluating the PRF on all points except X star. To preserve the functionality of the circuit, inside this block here, we're going to check if the input is equal to the puncturing point. If that's the case, we're going to output the true PRF output as a hard-coded value. Since we have an indistinguishability obfuscator here, we're obfuscating this whole block and the functionality has been preserved. We know the adversary has negligible, well, sub-exponential advantage in telling the difference. Next, we're going to replace this hard-coded value with a freshly chosen random bit string. Now, since this key has been punctured, knowing it does not allow the adversary to evaluate the PRF on the puncturing point X star, and so the true output should remain indistinguishable from a randomly chosen string. Now we're going to change the output of our circuit F at point X star, so it's equal to the output of circuit G at point X star. But since our circuit F is XORed with a randomly chosen bit string at this point, X star, this change should be undetectable by the adversary because a randomly chosen bit string XORed with a fixed bit string is non-distinguishable from a randomly chosen bit string. Next, we're going to do the previous two steps backwards. So first, we're going to replace the true PRF output here. Again, since this key has been punctured, this change should not be detectable by the adversary because knowing the punctured key does not allow the adversary to differentiate the true PRF output from a randomly chosen bit string. That's the point of puncturing. Next, we're going to put back the true PRF, the non-punctured PRF key back. And since the functionality of the circuit hasn't changed and we have an indistinguishability obfuscator here, this change should also not be detectable by the adversary. So now we have shown that changing the output of F at one point should not be detectable by the adversary except with sub-exponential probability. All that remains to be done is to do the same thing for all points in the domain. And since the probability of the adversary detecting the change for each point is at most a sub-exponential in our security parameter, which is the key length, the probability of the adversary detecting the change to the whole truth table should be at most negligible in the security parameter. So our mechanism indeed converts this whole block into a black box, and we have Canetti et al. To thank for the proof technique. Of course, the looming question is what the overhead of this mechanism is. Remember, we're talking about chips, which naturally need to be small and fast enough to be usable for practical applications. Unfortunately, to the best of our knowledge, a practical indistinguishability obfuscator for all circuits is far from being a reality. But we do have the option of using tools from the chip design domain, like binary decision diagrams. So a binary decision diagram is a representation of a Boolean circuit that is canonical, and due to the fact that it's canonical, it serves as an indistinguishability obfuscator. Binary decision diagrams don't really work for all circuits. They're known to be inefficient for certain classes of circuits, but they might be good enough for the types of circuits that hardware designers are concerned with. We're currently investigating this possibility. Of course, representing a pseudo-random function in the form of a BDD might just not be possible in practice, but we don't know yet if that's the case. That's it from my side. Thank you for taking the time to attend the virtual talk. I'll be happy to take any questions now.